Welcome to The Explainer. Today we're diving into a really powerful machine learning concept that all comes down to a simple question. When you need advice, is it better to trust one genius or a whole crowd of people? We're going to explore that idea through two major strategies, bagging and boosting.
So, let's start with something you already know. Think about a huge life decision, right? Like buying a house or switching careers. Do you go find the one smartest person you know and just do whatever they say? Or do you ask a bunch of people, friends, family, maybe a few experts, and then kind of blend all their advice together to make your own call? Yeah, most of us do the second one.
And you know what? That very idea, that the collective intelligence of a group is often way better than a single expert, that's the core principle behind what we call ensemble methods in machine learning.
In machine learning, this wisdom of the crowd helps us fight two big problems. The first is variance. That's when a model is way too sensitive to the specific data it was trained on. It's kind of like getting bad advice from one friend who had one really weird experience. The other problem is bias, where the model's just too simple and misses the big picture. By combining models, we average out those weird experiences and build a much more complete picture, getting us a lot closer to the right answer.
So, instead of putting all our eggs in one basket and building a single high-stakes model, an ensemble method takes our data and uses it to train many different models. Then it cleverly combines all of their predictions to create one final supermodel that's way more robust.
So, how do we actually build this crowd of models? Well, our first major strategy is a technique called bagging. You can think of it as putting together a team of independent thinkers.
Okay, bagging. It's short for bootstrap aggregating, which I know sounds super technical. But trust me, the idea is actually pretty straightforward. Imagine you give slightly different case files to a bunch of different detective teams. They all work on the problem at the same time, totally separate from each other, and then you just gather all their conclusions to make your final call.
Here's how it works in practice. We start with our original data set. From there, we create a bunch of resamples, and each of those little data sets is used to train its own independent model. Finally, the predictions from all those models are combined, usually by voting or just averaging them out, to get one powerful final answer.
Now, this process looks pretty simple on the surface, right? But there's a really subtle yet super important detail in this diagram that isn't quite right.
Take a second and look. Can you spot it? I'll give you a hint. Look closely at the size of those resamples compared to the original dataset on the left.
And the answer? It's all in that bootstrap part of the name. It means we sample our data with replacement. Imagine you have a hat full of names. You pick one out, write it down, and then you put it back in the hat before you draw the next one. This means each resample should actually be the exact same size as the original dataset, just with some data points showing up multiple times and others not at all.
So what's the bottom line here? Bagging is fantastic at reducing variance and the risk of overfitting, because any single weird data point is less likely to throw off the whole average. It's also really easy to scale up since all the models can be trained at the same time. The downside? It doesn't really learn from its own mistakes, and it's not designed to fix a model's underlying bias.
Okay, so that's a team of independent thinkers. But what if you could build a team that actually learns from each other's mistakes? Well, that's the whole philosophy behind our second strategy. Boosting.
With boosting, we're not working in parallel anymore. This is a sequential process, where models are built one after the other. Each new model is specifically trained to fix the mistakes that the model before it made. The best analogy is a master craftsman training an apprentice. The master points out the apprentice's mistakes, and the next apprentice focuses specifically on getting those tough parts right.
You can see this perfectly with a famous boosting algorithm called AdaBoost. Look here, the first simple model makes a few mistakes, right? You can see them circled. So in the next step, the algorithm forces the next model to pay more attention to those specific errors by giving them more weight. This just keeps going, with each new model laser-focused on fixing the mistakes of the one before it.
And this leads to a really fascinating trade-off. Because boosting is so obsessed with its errors, it can achieve incredibly high accuracy. But that intensity creates two problems. The whole process is sequential, so it's slower. And its obsession with fixing mistakes means there's a higher risk of overfitting, basically memorizing the training data instead of learning the general rules.
All right, so we've got two completely different philosophies here. On one side, the parallel teamwork of bagging. On the other, the sequential, step-by-step learning of boosting. Let's put them head-to-head.
And this visual just nails the difference, doesn't it? Up top, you've got bagging. It's parallel. You make your samples, build your independent models all at once, and then you average the results. It's like a single wave of effort.
But down below, you've got boosting. That's a chain reaction. The outcome of one model directly tells the next model what to focus on. It's all about that step-by-step improvement.
Let's just boil this all down. Bagging, it's a parallel process, and its main goal is to reduce variance. That's the risk of overfitting. That's your committee vote. Then you have boosting, totally sequential, and its whole purpose is to reduce bias, the risk of your model being too simple. That's your master and apprentice. See? Two different problems, two very different but very powerful solutions.
Okay, so after all this theory, you might be sitting there thinking, why does any of this actually matter? What's the real-world impact?
Well, it matters because these are not just abstract academic ideas. Ensemble methods are the engines humming away under the hood of some of the most critical tech we use every single day. They power the algorithms that give us more accurate weather forecasts, they help doctors make better medical diagnoses, and they build smarter financial models. They simply make the tools we rely on better.
Which, of course, brings us to the final big takeaway. After learning about these two powerful approaches, you're probably wondering, when is the right time to actually use them?
Well, the real answer isn't just use them. It's about using the right one for the right problem. Are you working with a complex model that's likely to overfit? Bagging can help stabilize it. Is your model a bit too simple and making some basic mistakes? Boosting can sharpen its accuracy. The ultimate takeaway is that in machine learning, teamwork, whether it's independent or corrective, almost always wins. The real question is, as these models get even more powerful, how do we make sure the wisdom of our machine crowds is always leading us in the right direction? Thanks for watching.